Saxon Algebra 1, Lesson 97. Welcome back, students. Here we are. Spring break is over. The midterm is over. And we are going to tackle the first of the last 6 weeks of lessons. If you're following along with my calendar, that means we are scheduled to be done with our lessons by Monday, May 23rd. This is a Monday. We'll review for the final. We'll take the final on the 25th to the 26th and be done before June begins. If you're working on a different schedule, just know you're 6 weeks from the end. So, yay team. All right, today we have a geometry topic and we're going to do some review before we jump into what's new. And what's new is interesting and cool. So let's start by talking about a line. A line is a series of points that lie next to each other with no gaps in between, going all the way to infinity in either direction. We know that lines have equations that describe the relationship between all of these points, and we know that the equation of the line will give you a way to calculate each and every point along this line if you so desire. We often look at two lines at a time, and we call these intersecting lines. They have different equations. They're both perfectly straight. They both go on to infinity. But when they intersect like this, they make what we call vertical angles. And vertical angles are super cool because they're always equal to each other. Right? This is equal to that angle. And what's cool is that a pair of intersecting lines will make two pairs of vertical angles, right? The top to bottom and the side to side angles are both vertical angles. Obviously not equal to each other, but they're each equal to the one across from them. All right, now what we're gonna do is zero in on just part of this picture, and we're gonna look at this area in closer detail. See how I just took this part and drew it here? We can look at this as segments of two lines, or another way to define it is to say here's a common point and these are two rays, right? A ray is a line, is a kind of a half line, right? It's got an end point on one end, but then it goes to infinity on the other. So we can think of two rays that come from a common point, and we call that an angle. Now, as John points out in the book, there are lots of different ways to think about angles and to imagine the picture, and he goes into some more detail if you're interested in doing some light reading on all the ways that angles can be defined. I'm not going to muddy the waters. I'm just going to tell you, you can think of an angle as part of two intersecting lines, or you can think of an angle as two rays coming from a common point. That's enough. We don't have to do more. Sometimes when we have intersecting lines, they meet more perfectly, right? These guys are kind of squished, but these guys are perfectly up and down, and when they meet, they form a right angle. Now, the cool thing about that is that if they form one right angle, they actually form four right angles, right? If we've drawn these carefully, we call this when two lines meet at a right angle to each other, we call that perpendicular. Okay, and we call these four areas, we call them quadrants. We'll be using that word a lot in the future. And we remember that this little symbol, this square in the corner, means that we have a right angle that is 90 degrees. Okay, so far so good. A little bit more. Right angles are going to become more and more precious to us as we go on. There's a whole study, there's a whole branch of mathematics that's focused on the study of right angles. We call it trigonometry. Year after next, that is what you'll be studying. This is Algebra 1, then there's Algebra 2, then there's what we call advanced mathematics, which is not just algebra, it's other things combined in like pre-cal and trigonometry. So we'll be studying right triangles in more detail as we go. A right triangle is nothing any fancier than a triangle where one corner is a right angle. There's one thing that's true about right angles that's true of all triangles. We're specifically talking about right triangles today, but this rule is true for all triangles. For all triangles, if you add up the three inside angles, we call them interior angles, but they're the ones on the inside of the triangle. And I'll show you that there are exterior angles too. But if you add up the three inside angles, they always equal 180 degrees. That's very helpful. We want to remember that. All right, when we have a right triangle, we give the sides some special names. We call the side that is opposite the right angle marker hypotenuse. And then the two sides that come out of the right angle, right? See how this one comes out of that part and this one comes out of that part? These are called the legs. And the two legs are fairly interchangeable in what I'm going to be telling you about. The hypotenuse, it's very important that you know which one is that. Again, look at the right angle symbol and then look across. That's where you'll find the hypotenuse. The legs come out of the right angle. We give letter names to these three sides when we have a right triangle and we're doing what we want to do. The legs we name A and B. It doesn't matter which one is A or which one is B, as long as we're sure that the legs are A and B. The hypotenuse needs to be C. Now, way back in the day, there was a jolly gentleman. We're talking about like 2000 BC. This is a long time ago that people were fooling around with this. The Egyptians started to look at these patterns and try to come up with what we're going to talk about. But the proof of this idea is normally attributed to a guy who was 6th century BC, so 500s. And his name was Pythagoras. He lived in a town on what we now call Italy, and he came up with this idea. His idea was that if you take this side, square it, add it to the other leg, square it, that will equal the hypotenuse squared. John shows you some weird pictures in the book where he attempts to prove this to you. It's too confusing. It makes no sense to me. When you get to advanced mathematics rather, we will do some proofs of this and you will see that it can be proven in lots of different ways that this is true. For now, I ask you to just trust me that this is true and that I will prove it to you later and you'll love it. This is called Pythagorean theorem. And it is a super useful tool. We're going to start putting it to use right now with some simple calculations. It allows us to solve for a missing side, right? If we have two of the sides, we can find the third. I want to tell you two other things right now. I want to remind you that this works for right triangles only. It does not work for just any garden variety triangle. Has to be a right triangle. And then the other thing I'm going to tell you is that we will often just use algebra. We don't even have to use algebra to rearrange this. We'll often see it as c squared equals a squared plus b squared. All I did was rearrange which side is which. So I just want to put that before your eyes so that when we start to look at it from this direction, you'll go, oh yeah, that's just Pythagorean theorem, kind of backwardsy. All right, so what we're going to do is we're going to use this. We'll use it in this form today. We're going to use this to work some problems. (97.1). How many examples are in this lesson? 1, 2, 3, 4, 5. They'll go fast though. And here's our Pythagy boy. Oops, that's equals. Remember, these two are the legs, and this side has to be the hypotenuse, okay? And you remember what I said, when you're looking at the picture, as long as you know that these are the legs, it doesn't matter which one's A and which one's B. This has to be the hypotenuse. Okay, 97.1. Given the triangle with the lengths of the sides as shown, use Pythagorean theorem to find A. All right, so I copied the picture. If you are looking at a problem and you immediately know what to do, and you don't need to draw the picture, go for it. If you are hesitating at all, by all means, draw the picture. It will help you. Now, I see that what we have here is a right triangle. Good. That means we can use Pythagorean. I see the right angle marker here, so I know that this is the hypotenuse, and that's the one that we call C. So I'm going to call that C. One of the legs is already called A. I like that. And so I'm going to call the other leg B. Now I know exactly how to plug these into this formula. I'll take the one that we call A, square it, add the one that we're calling B, which is 4, square it, and those are going to be equal to C squared. That is an equal sign with a mistake in it. It's not a plus minus sign. And that'll be equal to C squared, which we can plug in as 5. It's okay to not use buckets on these because there's no minus signs. A squared plus 16 equals 25. I just complete those squares. Subtract the 16. A squared equals 9. Now, this is exactly, let's see, what lesson was it? It was one of the lessons we just did. It's 96. Difference of two squares theorem. We know that we can look at this and quickly solve it as A equals plus or minus 3, right? We just learned how to do that in lesson 96. But here's the thing. In geometry, we can often rule out our negative solutions because, is there any way that the length of this is -3? No, that makes no sense. You can't have a negative number for the side of a triangle. So we can discard the negative root and simply say that A equals 3, and that's our final answer. Okay? I want you to show this step because this is algebraically correct. That's the right solution. It's just here we can discard that negative value because it can't be -3. That makes no sense. Moving on. Find K. All right. Oh, I'm sorry. Find side P. I was jumping ahead. Now, what John is doing to try to trip us out a little bit is he's drawing the triangles in some weird ways. This triangle is floating through the air like, I don't know, a ninja star or something that's been thrown. That's okay. Copy it. I'm just copying exactly what John is showing. And he wants us to find side P. Okay, that makes sense. Now, we just have to orient ourselves, and I've already given you the rules that will allow you to orient yourself. Find the right triangle symbol. The side opposite is the hypotenuse. So we're going to call P C. That tells us where to put it in our equation. The two sides coming out from the right angle marker are A and B. So label those accordingly. And now we're ready to go. Okay, so don't let this weird presentation freak you out. Just find the right angle marker. Opposite is the hypotenuse. The two sides coming out from it are the legs. All right, so what we have is 4 squared plus 5 squared equals C squared. We're gonna call this side P. We're gonna call it C so that it matches to this. But later we'll get a little fancy and we'll be like, it's fine, just throw the P in as the other side. So we're just setting them up like this so that we know exactly how to plug them in because we're just starting out. Okay, let's solve. This would be 16 plus 25 equals C squared. We add those together, we get 41 equals C squared. Okay, now we're at this point. Now we use our difference of two squares theorem and say this C must equal positive or negative square root of 41. 41 is not a perfect square, right? So we can't simplify it like we did when we had a perfect square. But we just leave it like this. We just say, oh, it's the square root of 41. Whatever weird number that is, we don't even care. We just know it's the square root of 41. And we have plus minus, but then I'm gonna skip over and eliminate that minus solution. Eventually, we'll just skip this step and go right to this. But today I wanna make sure you're showing this step because that is our difference of two squares theorem. And we wanna make sure that we understand that's how we're solving this. This is the right answer. Square root of 41, let's see, square root of 49 would be 7. So that means the length of this side is a little less than 7, and we can test that for reasonableness. If this side's 5 and this side's 4, then yeah, 7, that makes sense, doesn't it? It should be a little bit longer, but this shouldn't be 42. That would be too big, right? So that's a nice thing about geometry too, is that it makes sense. You can visualize it. And I want to say a word in geometry's defense. At this point in many students' careers, they kind of hate geometry because we've done all of those horrendous area of a circle, surface area of a circle, giant area problems where we're doing all those weird shapes. That's annoying. For most students, that's annoying, and I'll be honest, it's annoying to me too. But now, with Pythagorean theorem, we're entering a brave new world of geometry that is far less annoying. We don't have to deal with pi. We don't have to deal with crazy diagrams. We're doing more calculations with our geometry, and most students, including me, find it way more fun. 97.3, don't mind Grace, she's snoring. Well, that was kind of like a moany groan as she flipped over. Okay, this picture is also weird. John draws the triangle, what we would often consider to be upside down. I read somewhere that when we have floaty, like this other triangle we had, where it's kind of floating upside down, that's the way the ancients used to draw their triangles most of the time. We're used to seeing them with the sort of like a bottom. We're used to seeing them more like this, right? Or like this. They didn't draw them that way. They drew them all kinds of different floaty ways. Okay, ready? What? Square root of 61? That looks terrifying, doesn't it? But don't worry, it's going to be fine. Okay, so there's our k. Again, first step is to orient ourselves. There's the square root symbol. Opposite it is the hypotenuse. These two are the legs because they come out. We'll call 5a and we'll call k b. We're changing his name just so that he'll fit into the formula. Remember, these are the legs and this is the hypotenuse. Okay, we'll plug these in. A squared is 5 squared. B is k squared. That's where our variable is. Now this looks somewhat confusing, doesn't it? But let's see what happens. This we can fix as 25. Now, whenever we multiply a square root times itself, we get the number back. And we can write that as the square root of a number times the square root of the same number will always give us the number, because it's 2 pigs in a house equals 1 pig out of a house. That's basically what I'm trying to say here. So this will help us in situations like this, because we know that if we take the square root of 61 and square it, again, another way of looking at it is that those two cancel out. We just have 61. Subtract the 25. And we get k squared equals 36. Oh, that's a perfect square, isn't it? So we'll take the square root of both sides. And we get k equals plus or minus 6. We drop the negative root and we say that k must equal 6. We don't have units usually in these problems, but we could put a unit on there, right? Inches, centimeters, miles. What if that triangle was measured in miles? That would be big. It'd be like, you know, a crop, a field. Okay, one more of these, and then I'm gonna just give you a slight variation on what we're talking about. Here comes another upside downy triangle. Again, this is the way the ancients thought it was normal to draw triangles, where they're kind of upside down and the hypotenuse is kind of floating. And this time we're finding side M. 12, 8, and M. One reason it's very helpful to draw the triangles is it helps you get oriented to which are the legs and which are the hypotenuse. Right angle marker, opposite. That's my hypotenuse. These are my 2 legs coming out from the right angle marker. Doesn't matter which is A and B. I just go with whatever jumps in my brain first. 12 squared, there's our formula up there, plus 8 squared equals, I'm going to call it c squared. You could call it m squared. Once you get the hang of these, it's okay if you use the letter from the problem, but I'm keeping it super standardized to that. 12 squared, well, that's a big number. That's 144. Plus 8 squared, well, that's 64. Equals c squared. Now let's add these two together. We get 208 equals c squared. Now we use our difference of 2 squares theorems. We want to find the square root of both sides, right? Now, this is going to need some prime factoring, isn't it? What times what equals 208? Remember that when we're trying to simplify radicals, the best thing to do is make a prime factor tree. I'm going to do 2 times 104. And I'm going to do 2 times 52. And I'm going to do 2 times 26. And I'm going to do 2 times 13. So that tells me that I could write this square root sign as 2 times 2 times 2 times 2, uh-oh, I'm running out of room, times 13, right? So I have 2 pairs of pigs that I can bring out. They'll both come out here and I'll multiply them together. So my answer will be 4 on the outside, square root of 13. So I'm gonna write m equals, and I know that it's plus or minus 4 square root of 13. That's what the difference of two squares tells me to do. Now I'm gonna drop the minus and just say m equals 4 times the square root of 13. Started writing a 6 for absolutely no valid reason. 4 square root of 13 is the final answer. All right, so we use our skills with radicals to break these down. Okay, last step is to talk about 3 sizes of right triangles that are very helpful and useful. We see them over and over again when we're talking about Pythagorean theorem. We call them Pythagorean triples. And what they are 3 right triangles going from kind of small to medium sized. I'm not drawing them perfectly, but this will give us exactly what we need. Too big. All right, and John's telling us ahead of time that these sides are true, they work out. This is called a 3, 4, 5 right triangle. Okay, because the sides are 3, 4, and 5. That does work out when you use Pythagorean theorem. And sometimes we'll find triangles that maybe are like 9, 12, 15. And you can see I've just taken the 3 and the 4 and the 5 and multiplied each number by another number, in that case 3. So we can use proportions for these. This one is called the 6, 8, 10 right triangle. And this one is called the No, I did this wrong. I'll tell you why. Here, let me just do it, leave it like this. 6, 8, 10, and 9, 12, 15. You will see that this triangle is a 3, 4, 5 triangle times 2, right? I took 3, I multiplied it by 2 and I got 6. I took 4, multiplied it by 2 and got 8. Took the 5, multiplied it by 2 and got 10. So if I can see that these numbers fit this same pattern, which is another way of showing it right here, I know a quick and easy way to solve these sides. Okay, I can just use proportions. This one is the same way, where you can see I've taken my 3, 4, 5 triangle and I've multiplied each of the sides by 3. 3 times 3 is 9, 4 times 3 is 12, 5 times 3 is 15. So what I've done is I've taken the same basic triangle and then I've just multiplied up by 2 and then by 3 to get bigger triangles that are exactly proportional to my original 3, 4, 5 triangle. So it's helpful to memorize this 3, 4, 5 triangle because we can use it when we're dealing with bigger triangles if those bigger triangles just happen to have the same proportions. There are 3 triangles like this. The 3, 4, 5 triangle is one of them. There's another one. Honestly, the 3, 4, 5 is the most helpful, but I'll show you the other 2. This one is the 5, 13, 12 triangle, and this one is the 8, 17, 15, okay? So these proportions are different than this one, but these proportions do always work out. And so they're among the many triangles that can be memorized where the sides are all nice clean numbers. This is the 8, 15, 17. Now John has chosen these 3. This one's a no-brainer. This one's a really great one that you'll see again and again. These are kind of random and obscure, but he's asking us to use these in example 97.5, our last example for this lesson. He's saying use these to solve 3 triangles. So I'm just going to show them to you. He's giving you these pictures, and he's saying, look, I'm giving you 2 sides out of the 3. Use these reference triangles. That's what I would call these. These are reference triangles. Use the reference triangles to find the missing side. So all we have to do is look at the 2 sides he has given us, 5 and 12, and then figure out which of the 3 reference triangles has those sides in it. 5 and 12, well, that would be this one, right? 5 and 12. So that tells us that A must be equal to 13. So we're just comparing the triangles he gave us to the reference triangles that I've given you, and they're also right here. Here, this one's 8 and 17. So we just look for the reference triangle that has 8 and 17. There it is. The third side is 15. So we know that B equals 15. You're just comparing the pictures. This is the one I like the best. 8 and 10. And you go, well, now wait a minute. None of these triangles have 8 and 10. But then you remember, oh, we can multiply the numbers up too, right? So let's see, how does that compare? 8 is 4 times 2. 10 is 5 times 2. Oh, look, this triangle and this triangle are the same. We just flip this one over. So we know that this is 4 times 2, this is 5 times 2. So this side must be 3 times 2. So C equals 6. This is the only reference triangle I really care about. These 2 are obscure. We probably won't talk about them ever again. 3, 4, 5 does come up fairly often. So we've drawn the 3 reference triangles, or Pythagorean triples, they're called sometimes. The main thing I want you to know is that these exist. And again, these are on page 409, if that's helpful to you to look in the book and see them. Most interesting to me is taking this 3, 4, 5 triangle and blowing it up by multiplying each side by another number. We did it for 2 and we did it for 3. But you can do it with any number. So looking at this pattern is the most interesting and useful as we go forward. Okay, guess what? That's a very long lesson and it's finally done. Yay! Thank you. Goodbye.